Hey, welcome. Today, we're going to follow the entire life story of a molecule. I mean, everything from how its atoms first connect, how it gets a name, a blueprint, and then finally, its real 3D shape. So let's get right into it. So it all boils down to this one simple question, right? How do these separate individual atoms actually link up to become a single, stable molecule? That's the big mystery we're going to unravel together, step by step. We're going to break this journey down into four main parts. First, we'll see how the bond actually forms, the sharing is caring part. Then we'll figure out how it gets an official name. After that, we'll draw out its 2D map. And finally, we'll uncover its true final 3D shape.
Okay, so every story has a beginning, right? For a molecule, that beginning is the bond itself. This is the very first, most important step in a molecule's entire life. That moment when two atoms decide to team up.
So what exactly is this connection? Well, it's called a covalent bond, and it's what happens when two non-metal atoms get together and agree to share a pair of their electrons. This isn't about one atom stealing from another, not at all. It's all about teamwork.
Here's a super simple way to think about it. Imagine two friends who want to ride a bike. The friends are the atoms, and that bike they're sharing, well, that's the pair of electrons that holds them together. They both get to use it, so they stick together. That, in a nutshell, is a covalent bond.
But not all sharing is created equal. Sometimes atoms share just one pair of electrons. That's a single bond. Or they can share two pairs, making a double bond, or even three pairs for a triple bond. And it's just what you'd think. Like using more ropes to hold something together, a triple bond is way, way stronger than a single bond.
Okay, so our atoms are officially bonded. We've got a molecule. But now what? What do we actually call this thing? This brings us to the second stage of its life, getting a proper name. Its own identity.
The secret to naming these molecules is actually really simple. It all comes down to using special prefixes that are basically just atom counters. That's all they do. They just tell you how many of each atom you're looking at. And here are the counters right here. One atom gets the prefix mono. Two atoms, that's di. 3 is tri, 4 is tetra, and 5 is penta. Seriously, if you can count to 5, you can pretty much name any of these molecules. It really is that easy.
All right, so how do we put this into practice? It's a simple 3-step recipe. First, you just say the full name of the first element. Easy enough. Second, you use one of those prefixes to say how many of the second element there are. And third, you just change the ending of that second element to "-ide." That's it.
Okay, let's try a few. You'll see how easy this is. Take CO2. We have one carbon, so just carbon. Then we have two oxygens, so we use the prefix di and change oxygen to oxide. Boom, carbon dioxide. How about PCl5? That's one phosphorus and 5 chlorines becomes pentachloride. Phosphorus pentachloride. See? And for N2O4, we have two nitrogens, so this time we do use a prefix, dinitrogen, and 4 oxygens becomes tetraoxide. Dinitrogen tetraoxide. You got this.
So, our molecule is bonded, it's got a name. Now we need a map. We need to figure out how everything is laid out. And for that, we draw this really cool 2D blueprint called a Lewis structure.
A Lewis structure is just a simple diagram, but it shows us two really important things. First, it shows us exactly which atoms are connected to each other. And second, it shows us where all the electrons are. Not just the ones being shared in bonds, but also the other really important ones called lone pairs that are just kind of hanging out on an atom by themselves. So how do we know where all these electrons go? Well, the whole game is guided by one main idea, the octet rule. You can think of it as the #1 goal for most atoms. They just feel the most stable and, well, happy when they have 8 electrons surrounding them. Drawing one is basically a 4-step recipe. First, you add up all the available valence electrons from every atom. Then, you connect all the atoms together with simple single bonds. Third, you take all the leftover electrons and sprinkle them around the atoms until they all have 8. And if you run out of electrons before everyone's happy, that's when you have to make some atoms share more by creating double or triple bonds. Let's look at a real example. Good old water, H2O. The blueprint shows us we've got one oxygen atom in the middle, and it's bonded to 2 hydrogen atoms. Those are our 2 bonding pairs, the shared bikes. But look closely at the oxygen. It also has 2 other pairs of electrons that are not in a bond. These are the lone pairs. And pay attention to those guys because, spoiler alert, they're going to be a huge deal in our final step.
This 2D map is awesome, right? It tells us a lot. But it kind of makes you wonder, do molecules really exist as these flat little drawings just floating around in the world? Or is there something more to the story?
No way. Of course there's more to the story. That 2D blueprint is just the setup for the grand finale, the molecule's actual real-life 3D shape. And we can figure that out using something called VSEPR theory.
Now, VSEPR sounds super intimidating, I get it, but the idea behind it is so simple. All it means is that those groups of electrons around that central atom, they all have a negative charge, right? So they push away from each other, they repel. They just want to get as far apart from each other as they possibly can, and that pushing is what forces the molecule into its final 3D shape.
And this pushing, this repulsion, it results in a few really common shapes. If you have two groups of electrons, they'll make a straight line, a linear shape. If you have four groups, they spread out into this 3D shape called tetrahedral. But sometimes, like with water, we get this shape called bent. And why that happens is the whole key to understanding this.
Okay, here it is, the big secret. Remember those lone pairs from the water molecule? They are the game changers. Think of them like bullies on the playground. Because they aren't stuck between two atoms, they take up way more space and they push everything else away with more force. They literally squash the other bonds closer together, totally changing the molecule's shape.
And this makes it so clear. Look at methane on the left. It has 4 bonding pairs and 0 lone pairs. So they all repel each other equally and form a perfect, symmetrical tetrahedral shape. But now look at water. It also has 4 groups of electrons around the center, but 2 of them are those powerful lone pairs. And they push down on the 2 bonds, squishing the molecule out of that perfect shape and into its final bent form. It's all because of the lone pairs.
So there you have it, the whole story from start to finish. A molecule's life starts with covalent bonds. That's all about atoms sharing electrons. It gets its name by using prefixes, as simple atom counters. We draw its 2D blueprint with a Lewis structure. And finally, its true 3D shape is created by electron repulsion, something we figure out with VSEPR theory.
And that brings us to a final really cool idea. We just proved that those lone pairs force water into a bent shape. And in chemistry, a molecule's shape determines what it can do, its function. So what amazing things that are essential for every living thing on this planet, are only possible because the water molecule is bent and not straight. It's something to think about.